Hello everyone, Assalamu alaikum, welcome back. In this video, I will show you a code example of linear regression trained with the gradient descent. So gradient descent here, this would be regular gradient descent version. However, note that you can also do it using stochastic gradient descent. It's kind of interchangeable. And if you like, you can play around with it later on. Let's quickly revisit the linear regression model with gradient descent. So what we are doing is we are training this model here. So the training is up to this point, and then the threshold function is only used later on when we do the predictions of the class labels. That's after training. So for training, we don't need the threshold function. Let's quickly go to our notebook and start coding. Of course, you'll need some libraries to be initialized. And next I prepared toy dataset here, just some simple dataset containing two features x1 and x2. So tail is showing the last 5 lines of this dataset of CSV file, and there are 1000 training points. So you have two features x1 and x2 and one output value y. And this is a regression problem, so it's a continuous output value here. Now let's start by creating our design matrix in PyTorch, and let me write some code so we can discuss further. So here we have a design matrix consisting of the two features and then the class label as a separate tensor. I'm also shuffling the dataset. So I'm shuffling it and dividing it into a training and test set. So I'm again using this index trick that I explained to you earlier. Later we will be using the so-called data loaders when we use more complicated dataset like large image databases, where we have some automatic functions in PyTorch that do these steps for us. Here, I think it's sometimes good to just see how you would do that conceptually, like seeing or looking at the code to see what we are doing here. So what I'm doing here is I'm creating these shuffled indices. Let me show you how they look like here. So these shuffled indices are just the indices 1 to 1000 shuffled, and then I use them to select the training data. So first I'm actually using it to shuffle the data set. Here, this is just the shuffle indices. I select all the data points in the shuffled way for both the features and the labels. So note here, because we use this same shuffle index, they are shuffled in a way that is consistent. Because otherwise, if we use different shuffle indices, X might be shuffled differently than Y. And this is also why we can't just simply use this shuffle function that is implemented in NumPy or PyTorch, because the shuffle function would shuffle them individually. And then the features won't match to the corresponding labels anymore. And then I select 70% of the data. So this is just the size of how many data points are 70%. So this should be 700, right? Um, but this is just in general implementation that would work with any size of the data set. And yeah, this is how then I'm selecting the training and test set size. So the first 70%, the first 700 data points will be the training, and the remaining 30% will be for testing, and the same thing for labels. And then here I'm normalizing. So this procedure is also called standardization. It's kind of giving the data the properties of standard normal distribution. Well, it won't be standard normal distribution, so we don't change the shape of the distribution, but it will have the same parameters. That means it will have a zero mean and unit variance. Now let me write some more code, then we will talk. So now we have implemented our linear regression model. That is where it becomes more interesting. So we use this class-based implementation, because this is also something that we will be doing in PyTorch later for complex models. So PyTorch gives us a lot of convenience functions like convolutional layers, fully connected layers, and so forth. But we still apply the same concept by saying what our parameters are, and then how we use these parameters in which order. The backward function is later something PyTorch will implement us for automatically. So PyTorch will actually create this backward function for us. We don't have to do it ourselves. Here we do it ourselves because this is like a very low level implementation where I do things from scratch. In PyTorch later we can just use a fully connected layer and the backward function will be automatically done. But I think here for now it's maybe easier or like better for your understanding if we walk through this step by step and do it ourselves before we rely on automatic ways of doing that. So first we define the number of features in the initialization method, and then we assign the weights for our model. We just use zero weights, can be also small random numbers for this model. It doesn't matter. We initialize our weights. We need to know the number of features, right? So we use that information here because the number of weights depends on the number of input features. We have a separate bias unit because it's computationally easier to handle, so we don't have to modify the input features when we get them from the training set. So we also initialize it to 0. We only have one bias unit, so here's only one value, and then we compute the net inputs. So this is similar to the perceptron that we have used before. We multiply x, the feature, and the weights, and we add the bias. Okay, so then we have the activation. So the activations are just the net inputs because the activation function is a linear function. Then we get the activation. So now the view here is just to make sure that the shape is the same. So we have a singular value. So it's in one dimension, not two dimensions, just for convenience. And then now in the backwards method, what we are doing is we are computing the gradient. So remember the gradient is y. So the gradient of loss function with respect to y hat. So starting at back, what we are doing is it is done in two steps. So this is for our loss function. If our loss function is y hat minus y squared, then the derivative is 2 times y hat minus y, and then this should be the derivative. All right, so that's what we have here. And then we compute the gradient of y hat with respect to the weights, which was x, and the gradient of y hat with respect to bias minus 1. And then we put these two things together. So using the chain rule, the inner times the outer. We multiply the weights as a transpose with y hat. So this is a little bit tricky. All these types of things, the viewer and things of like that, this is really like to have to make dimensions match. So later on we won't have issues with that when we use PyTorch automatic functions because they will take care of it for us. If we do things manually, we always have to make sure that the dimensions are right. And then because we compute or we have gradient descent based on the whole training set, we divide by the size of the data set. This is basically for mean squared error instead of sum squared error. So this is our gradient of the loss with respect to the weights here, and this is the partial derivative of the loss with respect to the bias, and then we return the negative gradients. Now let's write some more code. Here we have a method where we compute the forward path, the predictions, and then we compute the negative gradients, and these gradients will be used for updating the weights to minimize the loss function. So here we have the training and evaluation functions, we have the loss function, and yeah, that's the mean squared error loss here. And here we are training our model. So now we have this for loop. This is a batch gradient descent. So we have the training function which takes our model, the input data, the number of epochs, and the learning rate. So we also keep track of the cost or loss function. I typed it as a cost here, but you can think of it as a loss. So what we do is we iterate over the epochs. So for each epoch we compute the predictions. This will be a vector. Y hat will be a vector because the predictions are for the whole data set. Then we compute the negative gradients using our backward model or method, and then we update the weights and the bias. This is the learning rate times the negative gradient. So that's how the update. So that's how we update the weights, and this is it. And then we go next. So here this is just for logging. We are just logging the loss, current loss, and print some outputs. We print which epoch we are currently in and the mean squared error loss, because then we can see whether it decreases or not. All right, let's define our model now. And let's now run this model. So here I am now calling this train function. uh, you can see that we start with a relatively high loss, like 1532. So you don't have to really pay attention to the absolute number. What you want to see is relative decrease, that it goes down over time. You can see the longer we train, the smaller the mean squared error becomes. So it's training here, and you can see there's a point where it doesn't go down any much. It says it stays at like 371. So that means it kind of converges and it has probably reached the global minimum. So what we see here, let's take a look at the plot. Let's write some code and plot the cost now. So you can see it starts out very large, then it goes down smoothly until it converges. So here at that point, we can say the model has converged. It has probably reached the global minimum of the loss function. So now after we train the model, we can now use it for prediction. So let's now predict on training set and the test set. Now this is similar to the training set, just for reference. Um, let's compute the mean squared error on the training set and then to the test set. All right, so you can see here the training set mean square error is lower than the test set mean square error, which means that the model is overfitting a little bit to the training set, but it's not too bad, I would say. Now let's also compare that with the analytical solution. So if you remember, in the analytical solution, we get the optimal weights using these matrices, the matrix inverse times x transpose y. This is the analytical solution. So let's compare our gradient descent solution with the analytical solution to see whether they match. So ideally they should be very close. Here are the model weights from our own model, from our gradient descent model. So we see for the weights, feature 1 weight is 0.36 and feature 2 weight is 37.9 approximately, and the bias is minus 0.54. Now here's the analytical solution. So when we execute that, you can see that this one and this one, they are very close. So we can see that this gradient descent implementation works and it gave us the global minimum here. I hope this was helpful. If you have any questions, feel free to drop a comment below. See you in the next video.